Industrial strain improvement has different objectives. It includes increasing the productivity, optimization of physical and nutritional needs of the organisms. But out of this, most important factor is to increase the yield of the product. In this session, I am going to talk about how to improve metabolite production. Both primary and secondary metabolite production can be increased using strain improvement strategies. Every organism has an innate tendency to limit the production of primary and secondary metabolites. An organism will produce these metabolites when and where it is needed. Further, the amount of these metabolites is finely controlled by a set of feedback system. And every metabolite pathway has two such systems called feedback inhibition and feedback repression. This system actually fine-tune the amount of metabolites produced by the organism, and its amount within the cell is controlled by this feedback inhibition and feedback repression. I'm sure that you have already have an idea about feedback inhibition and feedback repression. Here I am explaining this with a conceptual biochemical pathway. It is just like the pathway we studied in biochemistry, like the glycolysis. In the glycolysis, glucose is converted into pyruvate. In this pathway, in conceptual pathway, begins with the precursor A is converted to B is to C to D, and finally D is converted to E. So this is a hypothetical pathway, and this pathway you can see step by step each reaction is catalyzed by an enzyme. And in feedback inhibition, what happens is like the final product of the pathway is E. E is inhibiting the initial reaction. So the first reaction is conversion of A to B. This reaction is inhibited by the final product of the pathway E. So this is called the feedback inhibition. And this mechanism works by the final product E binds to the first enzyme and inhibit the activity of that enzyme. The enzyme responsible for the conversion of A to B, the E go and binds to that enzyme and reduce its activity. So once its activity is reduced, the flux through this pathway is reduced. So in case if a cell accumulates excess amount of E, it goes and binds to the first enzyme and reduce the flux through the pathway. So the production of E will be inhibited. Once the amount of E is reduced in the cell, what happens? The binding of the E to the enzyme is loosened and enzyme will be more active, so the flux through the pathway will be more and more E's will be produced. By this mechanism, end product is inhibiting or controlling the very first enzyme in the pathway, and it always need not be the very first reaction. It should be the committed step in a reaction. So the final product will be inhibiting the committed step. Committed step means the step in which there is a reaction with a high energy, so it is very difficult to reverse that reaction. Such type of reaction is called the committed step. So the committed step will be inhibited. In this hypothetical pathway, the very first reaction is the committed step. So E is inhibiting the very first reaction. So that's called the feedback inhibition. It is shown in the dotted line. Another mechanism is feedback repression. In feedback repression, the final product E is inhibiting each and every intermediate reaction. So in this example, show that it inhibits the conversion of D to E, C to D, B to C, and A to B. In real cases, it may not be inhibiting all this reaction, but it may be inhibiting couple of key reactions in the pathway. So in feedback repression, the final product is inhibiting intermediate reaction and the first reaction. So that's the difference between feedback inhibition and feedback repression. The feedback inhibition and feedback repression is to prevent the over accumulation of the product. The amount of product is increased. If the amount of product increases, it binds to the enzymes and inhibit the reaction, and the pathway flux through the pathway will be decreased, so production of E will be reduced. But in bioprocess industry, we want more product. We don't want the bacteria to produce minimum required amount of product. We want to produce maximum amount of product. In that case, in order to produce a high amount of product, we need to get rid of this feedback inhibition pathway and feedback repression pathway. If we take off these two pathways, our amount of product will be high. The organism tend to overproduce the product. So that in that way, the industry will become more profitable. So what we are going to do, we are actually disorganizing this pathway to get more of it. There is an innate tendency for the feedback inhibition and feedback repression. By different methods, we are overcoming this inhibition and repression to get better productivity. To improving metabolites, both primary and secondary metabolites, strain improvement use three different strategies. First one is removing the feedback molecule from the cell. We can remove the feedback molecule from the cell by increasing the permeability of cell. Secondly, preventing the production of inhibitor. The production of inhibitor itself is prevented. And finally, insensitivity to inhibitor. The enzyme which is responsible for the feedback inhibition and repression will become insensitive. So even in the presence of inhibitor, the inhibition doesn't happen. I'm going to explain these three in detail. First one, removing the feedback molecule from the cell. I'm taking the same conceptual pathway. In this case, A is converted to B, B to C, C to D, and D to finally E. In this case, we are removing E from the cell. The feedback inhibition and feedback repression happens only if the concentration of E within the cell increases to a certain extent. If it is below that level, feedback inhibition and feedback repression doesn't work. So what we will do is we will increase the permeability of cell for E. So once the product E is produced, it will be transported out to the outside cell. So inside concentration will be low, feedback inhibition and feedback repression doesn't happen. That's the first strategy. So it's just to increase the permeability of cell, so the feedback molecule will not be in the cell, so feedback mechanism doesn't work. One example of such strategy is glutamate production. Glutamate is produced by Corynebacterium glutamicum. So the Corynebacterium glutamicum, what we do, the final product is glutamate. This glutamate has such a tendency for feedback inhibition and repression. The mutant of this Corynebacterium glutamicum has high permeability to glutamate. So once the glutamate is produced inside such cell, it is quickly transported to the outside. So intercellular concentration of glutamate will be always low, and it is not enough to inhibit the reaction pathway. In that way, we can increase the yield of glutamate. The second strategy is the preventing the production of inhibitor. The same pathway, suppose our product of interest is D. We are not interested in E. In this pathway, we are taking an intermediate as our main product. We don't need the final product. In this pathway, feedback inhibition and repression is caused by the final product. In this strategy, what we do is we will mutate the enzyme which convert D to E. So this enzyme is mutated, the conversion of D to E is prevented. So no E is produced. If there is no E, the final product E, we don't have any feedback inhibition or feedback repression. So in that way also we can improve the product, improve the yield of the product. But one condition is that our product should be an intermediate product or an end product of a branch pathway. If our product of interest is E, we cannot do anything. But if our product of interest is D, we can inhibit the enzyme, we can mutate the enzyme which convert D to E and improve the productivity of D without feedback inhibition and feedback repression. These type of mutants can be isolated by enrichment and replica plating method. Example for this strategy is lysine production. I'll be explaining the amino acid synthesis pathway soon. The final strategy is to get insensitivity to the inhibitor. In the same pathway, E is the product which is inhibiting the first reaction A to B. What we will do is we make the enzyme which is responsible for the conversion of the A to B resistant to E. Even in the presence of this product E, this enzyme works perfectly. So the inhibition, the inhibitor is, our product is the inhibitor, the enzyme becomes insensitive to that inhibitor. Same things also applied for the feedback repression. The enzymes responsible for these steps will become insensitive to the inhibitor. And this type of mutants can be isolated by analog resistance assay. For example, Brevibacterium flavum is used for the production of lysine. If we isolate a bacteria which is resistant to S2 amino ethyl cysteine, the bacteria, Brevibacterium, which is resistant to the particular inhibitor, particular compound S2 amino ethyl cysteine, will be also insensitive to the lysine inhibition. So we can isolate and use it for the production. Another strategy is to use revertants. Revertants are the mutants which is reversed back to the original state. So another strategy to increase productivity of lysine, we take the Brevibacterium, and the first stage we will mutate all the Brevibacterium to get these bacteria which has a mutation in an enzyme homoserine dehydrogenase. So in the first step we take the bacteria, mutate and isolate the mutants which has defective homoserine dehydrogenase. And we will take this bacteria, the mutants, we will mutate them again to get homoserine dehydrogenase functional mutants. So at the first stage we look for the homoserine dehydrogenase negative bacteria, defective bacteria. We mutated it again and isolated homoserine dehydrogenase positive bacteria. This type of bacteria is called the revertants. They have reversed the mutation. In many cases, the first defect during the first time of mutation, the mutation occurs in somewhere in the homoserine dehydrogenase enzyme. Second mutation may not be occurring in the same site. It is occurring in a different site, but it regains its capacity to the function. So what happens is like the enzyme will get the activity of the enzymatic activity, but the feedback inhibition activity may be gone. So such type of bacteria is called the revertants. In that strategy can be used to isolate insensitivity to inhibitor. So what I said is, in the third strategy, the enzyme which is showing the feedback inhibition or repression will get insensitivity to the inhibitor. It can be isolated either by analog resistant mutants or by revertants. I am giving you an example of the process which is overproduction of amino acids. Amino acid is a primary metabolite which has several applications in food industry and as well as in the medicine. So we are taking the production of lysine. This is a pathway. It may be looks little bit complicated, but it is not that much complicated as it seems. The pathway begins from aspartate. Here you can see the aspartate. Aspartate is converted to aspartyl phosphate. Then aspartyl phosphate is converted to aspartyl semi-aldehyde. In this point, the pathway is split into two. One part goes for the lysine production. The another part is converted to homoserine. This homoserine can be converted into methionine, threonine, and isoleucine. So by this pathway, the organism produce 4 different amino acids: lysine, methionine, threonine, and isoleucine. Suppose we are going to produce lysine. We are not interested in methionine, threonine, or isoleucine. What should be our strategy? Where should the mutation should be? What all enzymes should be removed? So if I am going to produce lysine, one thing I should do, the aspartate, the amount of aspartate which is converted to aspartyl phosphate and aspartyl semi-aldehyde. A portion of it is converted to lysine and another portion is converted to isoleucine. So if I inhibit this enzyme, the enzyme which is converting aspartyl semi-aldehyde to homoserine, if I inhibit this enzyme, whole aspartyl semi-aldehyde will be converted to lysine. So I want an inhibition here. This enzyme should be inhibited when the methionine or threonine is produced. This is feedback repression and the dotted line is feedback inhibition. So I want this enzyme to be inhibited. If this enzyme is inhibited, what happens? The whole of the aspartyl semi-aldehyde will be converted or used for lysine production. So I can improve the lysine production by keeping this inhibition over here. And another use of this inhibition is that threonine is a feedback inhibitor of the very first step. So if the threonine is not produced, if this pathway is blocked, So the aspartate to aspartyl phosphate conversion will not be affected. Another thing I want, if I want an overproduction of lysine, is that the inhibition, the lysine itself is a feedback inhibitor. So the enzyme which is responsible for the conversion of aspartate to aspartyl phosphate should be insensitive to lysine. So for the lysine production, I want two different things. One, the enzyme which is converting aspartate semialdehyde to homoserine should be blocked so that all the aspartate semialdehyde will be converted to lysine. Secondly, the lysine may act as a feedback inhibitor. So the enzyme responsible for the conversion of aspartate to aspartyl phosphate should be insensitive due to lysine inhibition. In the same way, I can say if I want the methionine overproduction, I will do the different way. The enzyme which is responsible for the aspartyl semialdehyde to the lysine pathway, I want to block this step, and I want to reduce the amount of threonine. So the enzyme which is responsible for homoserine conversion to homoserine phosphate, this should be blocked, and so I can produce more of methionine. So if I want methionine, I want to block this step and this step. Okay, so in that way we can see, we can improve the productivity of each amino acid. If I want threonine, I maybe want other enzymes to be inhibited. I want this enzyme to be inhibited, and I want this enzyme to be inhibited. So it's all based on this pathway. So thank you so much. In the next session, I will be talking about how secondary metabolites production can be improved. Thank you.